Hello everybody, this is Mr. Walsh. I wanted to give you a tutorial on the graph program that I sent you a link for so you can see how you can use this program to find regression. So what I've created over here is a path that's actually on the field outside of our school. Now you could see this path that has these long, relatively straight sides. Those aren't that hard to find the length of, but the thing that's difficult to find would be this path over here. You could see it ends up being pretty curvy, and I'd imagine a lot of your paths will end up being having curves and things like this as well. And one great tool for approximating the path, a curvy path, would be to use polynomial regression. So I wanted to show you how you could do that with the graph program, as well as other regression if you wanted to use it. So what's going to happen here is this curvy part, we're going to actually want to find some key points and put those points on a coordinate plane. So first of all, I'm going to have this point be 0, 0, and what we're going to end up doing is essentially rotating so that the horizontal axis is going to be around here, okay? Kind of this blue line that's measuring right now, that's going to end up being our horizontal axis. You'll see in a second how that's going to work with in a PowerPoint. I'll show you in a second. So let's get some key points. So first of all, like I said, this right here is going to be 0, 0. Now, another point I'd like to get is this point right up here. So the points I'm looking to get are this point at this what will end up being a local maximum, this point which is going to end up being a local minimum, this point which is going to end up being a local maximum, and then this point right at this this kind of corner point here. Now, the more points you use, the better your polynomial regression will be, but these few points will actually work well in our specific case. So how am I going to come up with coordinates with that? Well, remember, this is going to count as 0, 0. This is going to be going horizontally. And if you notice, if I go about 75, that kind of gets me to where the local maximum would be. And this is where we have to be careful. When I click and move to the left, it keeps on measuring. That blue line keeps on measuring. So if I want to find what will be a y-coordinate, it turns out at around 130 feet. That's around where I kind of made this local maximum. Well, the y-coordinate here is going to be 130 minus 75 equals 55. Okay? And you'll see that on a PowerPoint in a second, because what's being measured right here is the entire, this first length plus this length that I went over there. So once again, let me do that for the other points as well. I click this ruler. Now if I go along this way, right, this is going to be my horizontal axis. At around 165 is about where I would get to the local minimum. And if I click down this way, making a right angle, right, which would be along my y-axis, at around about 225 is when I end up on here. So once again, what did I do? I went 225 minus 165, which equals 60. I went 60, and this is actually going to be in the negative y direction, so this is going to be related to a y-coordinate of negative 60. Let me do it couple more points. If I start at what we're calling 0, 0, I work my way up here. At around 275, it seems like I'm going to get close to this local maximum up here. And if I make a right angle to represent going along the y direction, at around 410-ish, I get to the local maximum there. So once again, this y-coordinate is going to relate to 410 minus 275, which is 135. And then finally, if I go from 0, 0, I go all the way this way. It's about 315 is going to be my related x-coordinate. That gets me all the way to the end here. And then I click and I go to the left, and to that 315 we added a number that took us to about 425. Okay, so what I do is say 425 minus 315 equals 110, and my y-coordinate here is going to be 110. So So that's what I did in order to find some of the measurements, the things that could act as coordinates. Now let me pull up my PowerPoint here, and you could see this is exactly what I did. So right here, this is our original map, our original path that was in our fields in the back of our school. I rotated it and enlarged it, and I put specific coordinate points to represent the points we found using the ruler tool before. As you can see, I rotated in such a way that we could think of this as some sort of a polynomial, where I, kind of go up and down this line this way. And then you could see the x and y coordinates related to what I found. So I have these points. The question is, how can I create a polynomial or some other graph that could accurately show this path? Well, that's where the graph program is going to come into play. So if I click my graph program, this is what it looks like. It's very user-friendly, very easy to use. Now you could see over here with my points, the x coordinates go as low as 0 and as high as 315. The y coordinates go as low as -60 and as high as 135. So what I'm going to do is I'm going to go a bit lower and a bit higher in the x and y coordinates in my window so that I could have all of the points of importance. Now, if I right-click where it says axes here, let me try that again, I could edit it. Now, in this edit, you could do pretty much everything you would want in relation to setting up the axes. So my minimum, instead of having my minimum x be 0, I'm going to actually have it be -50. You'll see, it'll make a little bit room, a little bit easier to see our points. And then the maximum, I'm going to make 50 more than 315, which is going to be 365. It's already set up to auto tick and auto grid, which will work for us. The thing I also want you to do though is to show the grid. The showing the grid will be interesting because well, you'll see it'll put a grid on the back here. Now on the y-axis, we go as low as -60, so I'm going to put -110, going to go 50 below that. And then the maximum, you could see on our graph, we go as high as 135. I'll add 50 to that to get to 185. Just so you know, you could change things like settings, show legend or not, where should the placement be, what should we know about the axes, font and color, you could change some different colors. So there's plenty you could do in here. Now when I click OK, I get, you can see I only have the X grid line. Let me go back to the Y-axis. I'm going to click Show Grid here too, so that we get the entire grid line there. So the next thing I'm going to do is plot these points. Now, if I go to Function and I go to Insert Point Series, that's going to allow me to plug in these points. So I click Insert Point Series, and I'm going to put these points 0, 0, 75, 55, 165, -60, 275, 135, and 315, 110. You could see you could change what the points look like, the style, the color, lots of things that you could check off here. But when I click OK, you could see my points. Okay, you can see the points that are involved. Let me just move this to the left here so that it doesn't confuse things. These are my 5 points. What I'm going to want to do is get make a graph that goes through these points in a similar shape to what you see here. And like I said, generally the best one will be a polynomial regression curve. So if you right click on series 1, it will say insert trend line. You click there and it gives you a lot of options. Now depending on what your points are, you may have things like logarithmic, power, and exponential come into play, but for the particular points that we used, it doesn't even show up as an option because it doesn't necessarily work with the graph we're using. Now with a polynomial model, officially, no matter where your points are, you could actually always create a polynomial that will go through all of the points that you clicked. So we have 5 points here, and 5 points would be all you need to find a unique quartic, meaning a polynomial of degree 4. And you'll see it doesn't, if I click on polynomial, it doesn't even allow me to go higher than degree 4 because these 5 points only tell you a unique quartic, not a unique polynomial of higher degree. If I added more points, I would be able to have a polynomial of higher degree. So that's what we're going to do. But just so you know, you have these 6 choices, but also if you click user defined, you have some other possible options for a model as well. Sinusoidal makes something that looks like a sine graph, a reciprocal function, rational function. So these are other things you may want to check out if you're interested. But a lot of times the polynomial will work best for us. I click OK, and this is what I get. You could actually see the curve if you look specifically at the points, and you'll see this on the next slide as well. It does actually, kind of sort of follow this same path. Once again, if we're not completely accurate, that's okay. We're looking for a roundabout idea of how long our paths are. Now, if you double-clicked here, you could actually see the exact formula for our regression curve. Just so you know, wherever you see a capital E, you could read capital E to mean times 10 to the whatever number. So capital E -7 means 7.2997 times 10 to the -7th. Okay, so that's it. That gets us our regression curve. And now let me show you the next slide. So I will minimize this. Oh, and just so you know, if you go to edit, you could copy the image. You could save this image. It's something you could put on a document or on your PowerPoint. Now, if I go to my last slide, you could see this is the final curve. And it does, not exactly match our curve here, but it does pretty closely match our curve here as well. So, it turns out this could potentially be a good measure of your path. And it's definitely something I want you to see. And the interesting thing here is you can actually test how well using your arc length formula works as compared to what the actual distance is, because you can use the arc length formula on this curve from 0 to 315. You could add the lengths of these straight lines, and if I'm going to go back to our map, if you look and you click on this, look at this. I called it sample path, but it actually tells you how many feet around your path is. All right, so Google actually tells that to you, so you could compare what Google says to the math that you actually did to see, how accurate your work ended up being. So in any case, that's how you can use the program graph to create graphs and to create a regression curve. So if you have any questions, please let me know. Thank you very much.